It's very fortunate that I give talk after Bob McPherson. It will be completely anti-McPhersonian talk, if you understand from the title. So it's smooth and compact. But before I want to start from something different, so the title of conference was some 2000, this number. Not really special number, but it ringed a bell. And I remember what it was, and it was a story 15 years ago. It's very small, but I can read it. It was Manin's talk, but Manin didn't give this talk. It was Sir Michael, I think, gave the talk on Arbeitstagung. In '84, it was new dimensional geometry, and there was a prediction here. So he wrote a space-time, which is, maybe I drew a bit bigger picture, so it has some kind of manifold dimensions. Then it has some kind of super fermions, and also has this prime numbers, which, in fact, later he speculated basically about point infinity here. So it was manifold how it should look next year. It's not exactly how it looks like, and it shows how it's impossible to predict. And also, he didn't predict that he'll be a director of Max Planck Institute in the year 2000. But it's still a great prediction because this year string theory didn't exist. Conformal field theory just was born in this year, and still he has pictures that what you have here get Keller and Stein manifold, or basically Calabi-Yau manifold. And there are some fermions, so there are some parts of picture for modern physics, what the manifold looks like. So my talk is, as you understand, probably is about manifolds, and Manin also talk about manifolds, and what he add point infinity just also to have it compact in arithmetic direction. So as I'll be talking about, I just want to apologize. There will be kind of essentially no content in my talk. Will be no theorems, basically no examples, just nothing. Okay, but but maybe we'll have some fun still. Yeah. So the idea of compact manifolds is kind of also the idea of 20th century. So some people like singular things, but mostly people look compact manifolds. And actually, I don't know what is compact manifold. Is it? So I have three theories. Is it an illusion of a comfort? So comfort, just to feel comfortable, yeah. Or maybe it's my theory is a tool for thinking about mathematical problems, and maybe it's really deep structure. And so I have these two basic properties. They're smooth and compact, and psychologically it's very pleasant. So smooth, it means something like it smoothes down, patted, and kind of nice local property. And compact, you can control it globally. So it's satisfactory from both points of view. And it's better to have both of them, of these properties, because if you have all the things together, then you get, at least in algebraic geometry, really nice things. You get Riemann-Roch, or index theorem. You get finiteness for homologies, and so you get a lot of finite dimensional vector space to play with, and finite dimensionals also. It's kind of algebraic analog of smooth and compact. And these properties are completely kind of hard to get them together. They're opposite, kind of dialectically opposite. And for example, algebraic geometry we have X of C. This is a scheme of variety. Then, if it's smooth, then on cohomology group, we have this hot structure, and this theory of weights, and weights are greater than k, and if it's compact, then weights will be lesser or equal to k, and
what are the weights?
Weights, there's theory of weights in cohomology. It appears, for example, if you translate situation to finite field, what will be powers of q in counting points and things like this. It's specifically algebraic geometric notion, not really intuitively clear. And
What is it?
there is some filtration on cohomology for any algebraic variety. It's theory of mixed hot structures, and the thing is filtered by.
So that you mean the further decomposition of these vector spaces?
Yes, it's kind of second grading, which we. So the idea of manifold seems to kind of 20th century idea, but in fact it's psychologically it's quite old. And when people played with actual functions, like Euler, and to understand function, it's to have its asymptotic expansion at every point. And every point, it means that you really compactify it, and it has some right coordinates to expand. So you get some intrinsic manifold, maybe with corners, to play with. And so just my philosophy, as explained, is completely anti-Macphersonian. So principle is singularities and non-compactness, some nth infinities, it's a mess, and we cannot really understand. We cannot do it, and to understand its things, it's to avoid this things. Of course, there is some noise which is our kind of residual mass which you cannot avoid. In Riemann-Zeta functions, there is some. Eventually, if you look deep inside, you'll find some random walk or kind of Brownian motions, and so it's not really possible. But noise probably should be understood something that we have our nice manifold and then approach. So it's still manifold, but here it's infinity, and here at the end we get dynamical system like this. Yeah, but it's out of my scope. Oh, I don't know. Now, if you have a function on real line, which is no C infinity function, but it goes. You don't know what's an asymptotic expansion infinity. I think you can glue it infinity.
Right. A boundless smooth function on the real line is like a dynamical system.
Yes.
It's shifting and shifting.
Yeah. But in algebraic geometry, these things shouldn't arise. And I was speaking about kind of framework of analytic algebraic series. So I will first speak about smoothness, and then a little bit about compactness and other stuff. So the slogan or principle, which is anti-Hironaka, anti-Macpherson, and so on. So the principle is that there is no singularities. Just as they don't exist. That's it.
Exactly what Hironaka did.
No. Singularities exist, and he wants to correct situation. But the claim is that there's nothing to correct. There's no singularities at all. That's just a priori. Yeah. That's.
See the principle for algebraic geometry was general.
I think it's a little bit more general even, yeah, for PD as well.
When people speak about galaxy mean we don't understand?
Yeah, just speak about wrong objects. It should be forbidden. Yeah. Okay. So it's actually in some not direct sense, not directly geometrically, but after some reformulation. So what no singularities of what? Of spaces. Yeah. So all spaces are manifolds. And so yesterday Joseph Bernstein already said the thing which I wanted to say, that manifolds are modular spaces. It's essentially one construction. But in fact, it's if you have modular space, it seems to be a priori have no reason to be a manifold. It could be something. And so, and the claim that modular spaces are intrinsically smooth. Just it's what I'll describe. It's kind of at least a level of formal power series. At each point, it's really smooth. So, and this thing which is slowly developing, it's kind of formal deformation theory. It's deformation theory of what? Essentially, of any algebraic objects of kind of algebraic nature. Maybe not so algebraic nature of. I can list think good objects which we can deform. First of all, one can deform algebras like Lie algebras, commutative, associative algebras, and so on. Modules of algebras, operands, so on. And there are schemes. Complex manifold. In fact, these formal things apply to C infinity manifolds. PDE. It's something going to write formulas eventually in some level. And so it's good things, and bad things are sets, graphs, groups, kind of discrete objects, kind of dynamical, maybe dynamical systems, I don't know. Good. And there is one unfortunate example which I still don't understand, how to deform motifs, which looks like objects from algebraic geometry, but somehow
They're bad.
They're bad, yeah.
Normal deformation.
Yeah, I have no idea. Nobody has any. Yeah, it's actually what Griffiths was thinking all years, what a parameter space of motifs, and general picture didn't give you any answer on this. Yeah, but so the formal deformation theory, I should mention some names. So it was started by Schlesinger, Elysée, and Gerstenhaber, Stashev. Yeah, so there was an important private letter of Deligne and another important private letter of Greenfield. So it was these things, but pictures slightly changes. So the idea is that the following: so kind of any kind of object which is good in this sense, any kind of algebraic object is called X. So first of all, for algebraic objects, it has sense about small deformations. The claim it gives some super manifold. Super manifold MX. I should put some adjectives. It will be Z-graded. So what means that the algebra functions is kind of complete. It will be symmetric algebra in some variables which have even weights. It's into the tensor exterior algebra on fermionic variables which have odd weights or odd grading in Z+1. Yeah, also this, because it's formal series, it will be formal. So it means that we work on level formal power series, so it will be completions here. Maybe infinite dimensions, maybe there are infinitely many. It's still possible to say. And yeah, but it still works. And then the main things will be a vector field. It will be odd vector field. So it will change parity of the grading, odd derivation of this algebra of degree +1, and satisfying equation that its commutative is self equal to 0, which is non-trivial identity in fermionic elements in the algebras.
Vector field means the derivation.
Derivation of this algebra, yeah. Also, this moduli space contains kind of base point. It will grow around one base point representing our manifolds to the kind of right moduli space, and vector field vanish in base point. So that's the whole geometry, and the claim is it's what we are doing in mathematics. It's just we constructed. It's kind of schizophrenic point of view, but what we are doing, we constructed more and more this. It's called Q manifolds. Q, it's come from physics, Veracity symmetry.
But this Q can this singularity, has singularity.
Yeah, it's also we studied singular point of vector fields, odd vector fields. There's nothing else.
This kind of singularity is accepted.
What?
I mean, your theory of
It's not singularity. It's zeros. But the object is. Oh, then of course when we make blow up of this and study it like in usual algebraic geometry. Yeah.
All mathematics about this one.
Yes. Yeah. So. No, all kind of mathematics close to algebra. Good. Yeah. Good in this local sense. Yeah. Yeah. What? Sorry.
What is exactly the statement of good mathematics?
Any objects, everything should be just collection of this supermanifold and some maps between them.
Only if it's not, it's not.
And nothing. Yeah. It's a kind of picture. I'll go a little bit now to later to the details how to construct these things, but it's really it's kind of another way to present.
Don't put words in his mouth. He said things close to algebra, the good things close to algebra,
Yeah.
can be re-expressed
Yeah.
in this language.
Yeah. Yeah. It's so what is mathematics? So there are different pictures. So what's this? Logic says it's kind of right. Kind of language, I don't know, formal language. Language, you write theorems, proofs, and so on. Yeah, and but it doesn't really. And one of the main features of mathematics is kind of self-duplicating. One can translate theorems in one situation to another situation, so kind of definitions. And it's not really fits here. There's things called model theory, but it's essentially no applications of it. So it's not right language. There was another thing that's called category theory and categories. So Joseph Bernstein started to take, let's consider model space of objects of categories. But yeah, it's actually super powerful things, but it's overstatement to see everywhere categories. It's kind of distortion of the vision. But at least it's kind of wrong, but at least what we have groupoids, naively. Any mathematical object has a group of symmetries. And essentially one thing which is left. In general, I don't know how to make. It's kind of artificial things to map one graph to another. You should make some choice, but on the map. Yeah, so I propose it's kind of vague picture that all things will consist of some manifolds, roughly speaking, nothing else. Yeah, so what are these manifolds? Let us kind of show one basic example how it comes from. and how it's related to deformations and so on. So one basic example is the following. Suppose we have a Lie algebra, which kind of Lie algebra of group of symmetries of some object. Then I can make some manifold, which is denoted by G, and according to proposal of Misha Gromov, I'll put 1 on the left. Shift functor. So what does it mean? And just graded vector space, which it has essentially no components. It's 0, 0. But in degree -1, you should put G. So, and homological algebra should always kind of remember put in -1 and hit ++1. So okay. So what is? Yeah, supermanifold and then completed 0 form, but this vector consider only small neighborhood of 0, and this formal neighborhood of 0 in this super vector space. And what is a vector field?
Is it graded vector space when an algebra at one spot and nothing anywhere?
Yeah. What is a vector field? So we have commutator. It has some structure constant. Let's choose basis. And get some structure constant, C, I, J, K. And the vector field will be the following. Q, it will be sum C, I, J, K. It will be only fermionic variables here. Okay. That's the definition. And it makes sense because it was Q-symmetric, but now fermionic variables, so it's a good quadratic polynomial here. And sorry?
Lie algebra super.
That's Lie algebra, say. Yeah. Then Q square equal to 0, so it's really most remarkable effect. It's the same as Jacobi identity. And kind of success of deformation series to realize that all possible identities which you write in algebra are Q square equals 0. This is one equation.
Maybe something's not clear. I mean, this vector space is like the manifold, and this other algebra is like the functions on the manifold, right?
Yeah, if you consider algebra functions, it will be co-chain complex of the algebra.
And then you have this vector field here.
Yeah. Yeah, and a little bit more general, if Q is linear term plus quadratic, just in general, in some coordinates, then it's the same as that we have a differential graded Lie algebra, which it was actually the main language of deformation series, that to any object we have associated differential graded Lie algebra up to some quasi-isomorphism. But if you look in detail, there's no really reason for this to be differential graded algebra. It's a kind of random fact that most equations which naively meet it are linear and quadratic. Condition for associativity is quadratic in multiplication. But if you go to a little bit more complicated example, you get non-quadratic equations. So it's right language is geometric language. And so how to see what the model
Code Lie algebra is the language of supermanifold.
Yeah.
An unnatural condition appears which you should go ahead and drop. You immediately have a big generalization.
Yeah, this is kind of strange. What's the property of this quadratic vector field? It's something not close on the bracket. It's not natural. Family, yeah. So, so now I'll try to draw some examples how associated this is deformation theory stuff. For example, we start from C infinity manifold. it has nothing but symmetries. And manifold is, you can see the vector fields on X, and again shifted by 1, this Lie algebra situation. And if you have complex manifold, then it will be differential graded Lie algebra shifted by 1, and this Lie algebra G has components which are vector fields in holomorphic direction d bar form and anti-holomorphic direction differentials d bar. Usual product, and if X is, let's see.
What are you describing now?
Examples, what, how to, with some object associated to this supermanifold. In all simple examples, it goes through differential graded Lie algebra and get.
You have seen infinity manifolds, and what do you know M?
You consider Lie algebra of vector fields on X. It's Lie algebra shifted by 1. Get this standard construction.
A little bit around differential.
No differential, no, nothing.
Yes, vector field.
Q is 0. Q is 0.
But what is 1? Are you just
Oh, it's the same as here. It's notation, yeah.
Yeah, but the question, what is Q?
Q coming from bracket. I explained this example of Lie algebras. And
These are still the algebra.
yeah, it's still Lie algebra.
These examples are special cases of that example.
Yeah. And complex manifolds gives differential graded Lie algebra, so it's essentially the same formula works. And if X is algebra, then we get Kersten hypercomplex, so GK will be home. And with some bracket and so on and so forth. So one can develop machinery and try to see. For example, this machine is also an object of mathematical objects. One can see, try to describe deformation theory of this machinery. And fortunately for us, we calculate with Jan V.Milman, for example, notion of operator seems to be rigid. So one can go, one cannot really go deep inside. So here's a picture, and so this, so we get this is formally supermanifolds, and what's the relation with real life? Usual deformations are the following. First of all, consider points in this mx point. You consider a set of points where q vanishes. So this will be certain z.
It's hard to define the deformation theory for a general supermanifold.
No. For general. In terms of general supermanifold. You consider points where this vector field vanish, and it's probably singular thing, but sitting in our nice right space. And but then it has some singular foliation. Namely, one consider commutators of V with Q with any vector field. On moduli space. These vector fields are commute with Q. It's simple issue of Jacobi identity. So they commute with Q, so they define something which defined in terms of Q, so they preserve Z. And it's easy to see that the form kind of satisfy, gives a tangent to some singular foliation on these things. And what we are considering, we're taking quotient space, which is extremely bad. So this is usual modular space, and this, you see why it's bad, because it's first we'll write some system of equations and then mod out. Yeah, by the way, that's actually a very nice feature here. So you see that it shows that kind of all natural system of equations have the same number of equations is equal to number of variables. If you write equation q is equal to 0, effectively should be one kind of isolated set of solution because it's a vector field. It's number of components of vector field is the same as number of variables. Sorry? Yeah. So about infinite dimensions, the story is the following. So one can make describe it's very easy. Some theory of some homotopy invariant, homotopy equivalence of such things, and okay, maybe just remove some piece. Yes? Oh, I can see the taking quotient space of Z by foliation, by singular foliation, given by this vector field. This vector, and it's usual deformations of algebra structure. Foliation spanned by and we get all V. It's V vary, yeah, all for all V. V vary.
And what is the definition of Z? Seems to make no sense. I do think it's geometrical that that only had one point.
Yes, no, but in logic geometry one can speak about families depending on some formal parameters, and then manifold will have points, and it's yeah. I'm sorry, my talk is extremely lousy. There will be no precise definitions. Forgot what was I going to. Yeah, about finite dimensions, the story is the following. It's easy to see that enough to consider linear part of Q at base point. So we get operator. Because it preserves the base point, so part of Taylor expansion of Q at base point, the base point, kind of in MX. So we get some operator, which is an endomorphism of the tangent space of the space point. And it's also of degree +1, and square of this operator is 0. So it's differential. And so the finite dimensionality is finite, as one can make finite dimensional model of this, its equation spaces cohomology are finite dimensional. And in practice, this guarantees by the fact that you start with some problems formulated again in terms of smooth compact manifolds, where you get ellipticity of finite dimensional vector spaces and good classes of algebraic structures. So in kind of this words of smooth compact manifolds, it should come automatically, this finite dimensionality. Yeah, so this is essentially all which I can say about smoothness now. It's only a very preliminary picture because it's on level formal power series, and Misha Kapranov wrote some papers when he tried to, in some examples, to get global thing of it. So I'll speak about compactness, and here it's kind of less clear picture. Here, for smoothness, the claim is somehow if you describe object, then you get intrinsically this stuff, just for free. If you analyze definition to any small details, you can extract this deformation theory, which originally was thought in each example you should work out some technologies, but it seems that there is a universal technology to do it. And for compactness, the picture is not clear, but it is to deal with geometric problems. My feeling is also that you get for free compactifications of modular spaces, just from descriptions. And it's not compactification from something like geometric invariance theory, but you look through the ideas is kind of very general idea. It's just everywhere. If something bad going on, bad is going to happen. And change scale and look through microscope. And then it probably repeats it. If it will be again something bad, then repeat it again. About how many times you should repeat it? Interesting. Yeah, it's kind of unclear. Yeah, I think it's. If you go to examples, it's sometimes non-isotropic microscopic, nilpotent, graded Lie algebras, and so on. And let me just show some example in real analysis. So let's consider a set of probability distributions on R. Yeah, and so it's nice set. It's not compact because R is not compact, but usually we have some variables that don't know what's, and you do some limits theorem. You don't know what truly scale, what's the center of the theorem. You apply, you want to divide by a fine group. Real numbers with positive dilation coefficient. And the action is not totally free. It looks like a free action, but it's not free because and this one that thinks it's delta function of x dx, x minus x0. On this measures, the action is not free. So I want to define another thing, which is well, it's kind of point mass, yeah. So that's modular space, and here it means that it really didn't look
stabilized by A.
Yeah, it's stabilized by A, yeah. In detail. So I want to describe a different space which is compact, which is very close to this. And it's compact. And the space is the following. So what is the probability distribution? Probability distribution gives you a function, f of x, f from real lines to 0, 1, which is, say, left continuous, and f minus infinity, it goes to 0, at plus infinity, it goes to 1. So it's probability that you see it in some in array, but this function can have in monotone, yeah. But these functions could be discontinuous, yeah, sorry. Yeah. Yeah, and these things will consist of functions which are continuous function, and it's very easy to write. So I'll describe it as a set. You consider a set of such functions. And we will, again, up to affine transformations. Such functions, such that f is not just one-step function, is not equal to such function at some point x0. So its derivative is not delta function 0. So it has some singularities. So f is equal to has some singularities, and at jumps of this function, you put an element of m prime. So it means that if you look through, again, rescale your horizontal variable and rescale vertical variable, so it will be probability distribution, and still gain something nice. So it's effectively functions are continuous functions. So just here it will be some hidden continuous function. And yeah, it's kind of recursive definition because I defined m prime in terms of m prime, and one can see that altogether we get some countable trees, well-ordered trees. It's still countable, and that will be this nice compact. Yeah, so it's very similar to stable curves in algebraic geometry, but in different setting. And analogous things one can describe for convex space of convex sets. And one can make convex sets always C1 boundary, for example, with analogous things. And yeah, so it's a general philosophy. It can be applied in many situations, so, but not always, I'm afraid. And it gives different configurations from what people usually look for. For example, in
describe some compactification of the space probability measures.
Yes.
So you add something else.
Yeah, I remove delta functions and add something else, and then we'll get compact. And
Can you explain it? And you add again the same thing? Or?
the same thing, yeah. It's at each jump.
Oh, we can back through the microscope.
Yeah, look at microscope in two directions. Yeah.
Very strong microscope.
Yeah, very strong. Yeah. Yeah. For example, this.
What's the connection between the supermanifold idea and this idea?
Yeah, so one should kind of join things together, and the problem is kind of to combine these things and compactifications via microscope or something else, and this super smoothness. The situation is the following. If, for example, I consider vector bundles, X will be algebraic variety. And we're interested, for example, in vector bundles on this algebraic variety. Then for deformations, what is responsible? We have cohomology of X is endomorphism group, which is finite dimensional. So varieties, again, smooth and compact, is finite dimensional. So we get usual deformations are governed by H1. Then we have H2, which is fermionic, which shouldn't compactify fermions. But then we get H3. So we get something like H3 bundle with fiber H3 over usual moduli spaces. So we should compactify it in H3 direction. I have absolutely no idea. It's kind of challenge for imagination what kind of energy ideas or whatever should give compactification H3. And why it's really will be nice to have it if you'll. So up to now, this whole program works only in low dimensional situation where you have no H3. When you have usual moduli space and maybe some fermions floating around. And then we get Donaldson invariance, Gromov-Peter invariance, and we can kind of count.
What's the connection between this compactification idea and the formalism of converting these problems into supermanifolds?
There are two different things, but compactification should be also be in smart way using this. As neighborhoods of this compactification will be some, again, super manifold.
So first it was a local step and now it's a global step.
Yeah, global step, yeah. I have no idea how to this compactify it along H3.
You think about this as one direction.
No, H3 is again even direction.
H3 can do it.
H3, H5 will be in directions. Yeah, and if it will be achieved, it will be really wonderful because then we can, so that's what we'll get. We get some compact singular space. But actually it will be, and it will be kind of fermionic bundle, vector bundle on it. In general, it could be singular, yeah, but in the usual sense, yeah. But it will sit morally in some super manifold. And then dimensions of, real dimensions of the 6 dimensions, so number of bosons minus number of fermions is index of some operator. It's something computable. And in this situation, people know now how to define some fundamental class. We can treat it manifold. It has tangent bundle. Sorry? Oh, it's odd and even variables. Now, it's a typical example if you... yeah.
But this cohomology, they kind of local, yeah? They be at one point.
Yeah, they be at one point, but the index will not change.
You want to say just knowing this cohomology at one point just tell you something about the whole space?
No.
Is a local object.
No, it's local object. It tells me nothing. But no, the picture, kind of fictitious picture, is that after compactification you get, you realize your manifold. Eventually, you realize your modular space after compactification with all this bosonic part will be zeros of sections of a vector bundle on some manifold. It will be a compact set of zeros. And
don't you want in particular that just looking at Taylor expansion to a certain manifold at one point, you can have embedding in the formal space now? Because you start with 1 point, all information at 1 point.
It was at 1 point, yeah, but now I wanted to kind of...
How extended? You never said about
at any point will be locally the same. So if you have at 1 point, then you have a nearby point as well. And it will be kind of Schifo.
You don't speak about the global modular space, no?
Yeah, no, the global modular space, in some examples one can work it out, like for stable curves or maps and so on. And it's near each point, this is picture, and they're compatible up to suitable notion of homotopy. Yeah, so that's this kind of project to extend the theory of kind of Gromov invariance to all questions in geometry. So we formulate things and we get some cobordism class. And let me say just one remark that maybe 2 remarks. So what's going on in other things? So it was about kind of algebraic geometry or algebra. And so there's physics, I mean kind of quantum field theory. And maybe something more general. In physics, it seems that kind of intrinsically smooth. So there's no singularities. If you consider modular space of quantum field series, it seems to be just for internal reasons have no singularities, so no singularities are allowed. So of course it's again in real life there are singularities, you get some parameters, some branching, but all is emerged in some bigger infinite dimensional manifold. Just one of the reasons why it's going on is the following. So one can try formalize in different ways with quantum field series and eventually get the following. You get kind of space-time manifold like R4 or whatever, and over each you have a infinite dimensional vector bundle with flat connection, local fields at each point. This connection is spherical to 0. It's essentially kind of 3D module of infinite rank. And then this corresponding manifold responsible for deformation theory all sits in negative dimensions, turns out. So it will be sections of y times d form on maybe x. Nice. So here are densities of Lagrangians defined up to derivatives. And here you get internal symmetries of 0 and so on. So you get some homotopy type in usual topological sense. But there's nothing in positive part, so there's no abstractions. So not in only the super sense, but in kind of plane sense, I think is smooth. But unfortunately, if one tries to think why it's not, it seems that it's also intrinsically non-compact in physics. In some simple situations, it's compact, and that's how Zyberg-Witten and all these things appear, because people just make stronger and stronger interactions. They don't understand what's going on, but they believe it's still a simple system. So you live inside of virtual simple system, which is, and there's no infinity. But in real life, there's infinity, which is kind of chemistry, then go to biology, and so on. That's, I can't really understand these things up to the end, so this is this issue of non-compactness in physics. So maybe I'll stop.
Psychology at the bottom.
Yeah, it's far away. Yeah, it's somewhere. Huh?
Probably, what's your example of the manifold corresponding to PDEs? You didn't say.
No, the thing is the following. If you have system of equations, this is one remark. You have system of equations, some fi of x equal to 0. Then you make supermanifold just in a very formal way. You consider coordinates x and psi I. And vector field will be, I think, sum of f of x divided psi I. It's spherical to 0 by trivial reasons. But if you have overdetermined system of equations, and somehow you know that there still are solutions, so there should be reasons, and all this built in nice, again, supermanifold. It's called BRST usually in physics.
I think we can postpone to the equation
discussion. Okay.
But the next lecture will be